Welcome back, everyone. I hope you're doing well today, staying warm and dry. I'm recording this when we're having ice and snow, so I hope you're staying warm and dry and enjoying our conversations on double displacement precipitation reactions. We're going to do two more examples to use our double displacement precipitation reaction skills to predict molecular, total, and net ionic equations. Before we do that, I love to show this slide because it speaks to an important point when writing molecular total and net ionic equations, which is particularly with the total and net ionic equations, making sure that you note the state and charge of a particular species. And now, why is that important? Isn't sodium always sodium? Well, it is true that elements are identified by their number of protons, but the reactivity of species as ions versus elements can be really different. For example, with sodium. Sodium as an ion, as a +1 charge, is very, very stable. It's very easily, very stable in aqueous solution, not very reactive at all. However, sodium by itself as an uncharged atom, as an element, is very reactive. There's a reason why sodium wasn't given to you as an unknown metal in the metal experiments, because it reacts violently with water. So all of this is to say that for the exam, and when you do practice problems, when you write the total and net ionic equations for species, I'm going to be looking for you to say, or for you to write for each species what its state is, solid, liquid, gas, or aqueous, and if it is a charged species or not. So keep that in mind. Remember about the little puppy and the monster. Let's go ahead and let's do two examples. So let's say I was to give you these two reactants, and I asked for the balanced molecular ionic, and when I say ionic equation, I mean total ionic equation, and net ionic equation for the following reactants. And we've got silver nitrate and calcium bromide. Let me get my little pen again. So you may or may not be getting comfortable with predicting products without the little crisscross. If you are, great. If not, feel free to go ahead and do the crisscross. I'm going to do the crisscross to make sure that I know that my first cation is silver, my second is nitrate, my third is calcium, which has a +2 charge. And now, what is my anion here? My anion is Br. It's not Br2. That subscript 2 is there in the molecule to balance out the charge. The charge on just bromine is -1. So that's what I'm going to put in my little crisscross here, so I can easily see that, oh, I'm going to need 1 silver and 1 bromine. I'm also, for one of my products, I'm also going to need to pair that calcium with the NO3. But since nitrate has a -1 charge and calcium has a +2 charge, I'm going to need 2 nitrates to balance out the charge for that molecule. And remember, always when you put ions together to form a neutral species, always, always, always subscripts. And since we have more than one polyatomic, we need to put parentheses around the polyatomic. So our second product is Ca parentheses NO3 subscript 2. So those are the two products for this molecular equation, which is not yet balanced. Still need to determine the state and balance it, but let's go ahead and do the states. Silver bromide, from your solubility rules, is a solid. It's insoluble. All nitrates are soluble according to your solubility rules, so AQ. Now let's go ahead and balance this equation, because we need to have the balanced molecular equation. And I see fairly quickly that I've got 1 NO3, 1 nitrate, and 2 over here. So I'm going to need to put a 2 over by the silver nitrate. So my nitrates are now happy, but that also means I need to put a 2 in front of the silver bromide. And that works out great because, hey, on my reactant side, I have 2 bromines. So what we have here, what we've just finished, this is the molecular equation for this double displacement reaction that is also a precipitation reaction because we formed a solid from 2 aqueous compounds. Now it's time to do the ionic or the total ionic equation. If you remember, to do ionic equations, we focus on the species that are aqueous. Those species get split up in the ionic equation into their cations and anions. So looking at the first species, we've got silver nitrate. So we're going to have silver ions and nitrate anions. But we got to remember, because we want to keep our balanced equation, we got to remember we've got this 2 here. So that means I'm going to have 2 silver ions that are aqueous and 2 nitrate anions that are aqueous. So coefficients that are out front of a molecule, when you have to split that, if you have to split that molecule up into ions, make sure that that 2 goes to everything behind that particular molecule. We've got 2 silvers and 2 NO3s. So that's the first part of our ionic equation, at least for our first reactant. Now we got to do the calcium bromide. So, well, looking at that, I know I've got 1 calcium. I've got bromine. How many bromines in that calcium bromide do I have? I've got 2 of them, right? Because for every 1 calcium, there's 2 bromines. So when writing that as an ion, that subscript 2 actually comes up front. So I have 1 calcium, that's a +2 aqueous, and 2 bromines. So that 2 becomes a coefficient for the bromine. So now I have split up my second aqueous reactant. For my product, I have my silver bromide as a solid, so that's going to stay together. So I'm still have I just write down my 2 AgBr solid. And then for my final for my final product that is soluble, I split that up into its component cations and anions, realizing that I have 2 NO3s and that 2 becomes a coefficient in the ionic equation. So what I have written here, this whole big long strand, this big 2 strands, I guess, this whole thing is the total ionic equation. And so looking at that total ionic equation, the next step is to do the net ionic equation, which means cancel out the ions that are the same on both sides. I see 2 NO3s on this side and 2 NO3 on this side. I see 1 calcium and 1 calcium. So I'm going to cancel those out as spectator ions, and what I am left with is this reaction down here, which is essentially the total ionic equation minus the spectator ions, to give me the net ionic equation, or NIE. Okay. So you should feel comfortable being able to use your skills to write molecular, total, and net ionic equations. Let's do one more. Why not, right? It's cold out, nowhere else to go. Let's do one more. We've got potassium carbonate and magnesium chloride. Let's go ahead. I'm going to do my little crisscross down here, I think. Looking at my cation and anion for each, I see my cation is potassium. I've got 2 of them, but remember that subscript 2 is there just to balance the charge. My cation is just potassium. My anion is carbonate, that polyatomic groupie. Carbonate has a -2 charge. So remember, there's a lot of skills that you use in these problems. A lot of skills, particularly from your first unit, names and charges of mono and polyatomic ions. So that's the cation and anion for my first, the cation for my second reactant, magnesium +2. My anion is Cl, chlorine, which has a -1 charge. That 2 is just there to balance out the charge for the molecule magnesium chloride. And doing my little crisscross, and I know I've kind of got written small here, but I can see that my products are going to be KCl, 1 potassium, 1 chloride only needed, so the charge equals 0, plus magnesium carbonate. Magnesium's a +2, carbonate's a -2, so I just need 1 of each. Using the solubility rules, I see potassium chloride is aqueous and magnesium carbonate is insoluble. Things that are insoluble get an S. One more thing to do to get this molecular equation balanced is to add a great big fat 2 in front of the KCl to balance out my potassiums and chlorines. So that is my molecular equation, my balanced molecular equation for this problem. Next is the total ionic equation, remembering to focus on the species that are aqueous. Split those up into their cations and anions, making sure you keep track of coefficients and subscripts of monoatomic ions. In potassium carbonate, my cation is potassium K+, but I have 2 of them, so that 2 comes out front. I've got 2 potassiums and 1 carbonate anion. 1 magnesium and 2, because of that subscript, 2 chloride ions. 2 potassiums and 2 chlorides from the 2 KCl on my product side. And the magnesium carbonate stays together because it is a solid. So what I have written on this second line, along with the magnesium carbonate solid, that is my total ionic equation. Last but not least, cancel out the spectator ions, the ions that are the same on both the reactant and product side, and what you are left with is the net ionic equation. Well, I see I've got 2 potassiums, I have 2 chlorides on both the reactant and product side, so what's left is the carbonate anion reacting with the magnesium cation to give the net ionic equation. So there are several more examples in your worksheet that I have put on Canvas. There are some that are also on your MindTap. I would encourage you to try your hand at those in using your skills to determine molecular, total, and net ionic equations for double displacement reactions.